all of that, we are going to go ahead and kick things off because I actually have a huge amount of content to cover over the next hour. So again, thank you all for joining me. This is actually the second webinar in our series. Yes, this will be available. The video will be available later. And thank you for asking questions like that. As Mike mentioned, there is a Q&A section that you can access via the bottom that will let you ask me questions throughout this time that I can see, and I can help deliver all of that. So that said, keep asking questions. It's why we do it. Today, my goal is to talk about RTK, PPK, GPS, the broader category of drone GPS, all of the technologies and workflows that are used to get high precision data from the GPS out of your drone. And as Mike mentioned, this actually was derived from our last webinar that we did on flight operations, because there clearly is a lot of different there's a little bit of confusion about what high precision drone GPS can do, what RTK means, what PPK means, which one's better, what are the right circumstances. So we're going to go through all of that. And in order to do so, first make sure my keyboard works right, we are going to do a deep dive into drone GPS, including covering all of the miserable acronyms that are involved. We are going to cover things like GPS, GNSS, RTK, PPK, SPP, IMU, GCPs, NOAA core stations, OPIS, NTRIP, VRS, SASIMs, RINEX, RTCM, WTF. There are too many acronyms. And everyone that works here at Aerotos actually knows that I really hate acronyms. I feel like they really don't do a good job of communicating things to people, especially for younger or newer employees. And there are so many misconceptions. Most of these acronyms are used improperly. And quite frankly, I often use them improperly too, because that's just how colloquially they are used. And in fact, when people say RTK, they really rarely mean RTK, but we'll cover all of those acronyms and what they really mean and how to use them in just a little bit. Then, once we get through the actual technology side of things, I always like to start on a little bit more academic basis. This is how I do things for my presentations. We're going to start very academic to make sure that we all have a similar baseline understanding of what the technology is, how it works from a technical standpoint. And then we're going to move into, okay, how do we apply it? How do we set up this system? What hardware do you have? What hardware do you want? What base station do you need? What RTK and PPK and post-processing GNSS workflows do you need to achieve the workflow reliability, the accuracy, the usability that you actually want? And from there, the last step of that is going to tie it all together. We're going to touch on the actual data processing, when you actually integrate it all into photogrammetry, into LiDAR, to get to the end solution, which is, of course, a map. At least that's what we think the end solution ought to be for this sort of thing. A little bit about us, why we do this. Aerotos, for those of you that aren't familiar, we do drone data processing for surveyors. We've been doing it for a decade now. Our business model is you, the surveyor, would fly a drone, send data to us, we process it and send it back a map. And of course, that gives us a very unique perspective, because we have seen tens of thousands of drone survey projects across every different permutation of GNSS setup that you can imagine. And that means we've seen some that are very, very good and some that are very, very bad. Some that are complex, some that are simple. And all of the information that is here is not, while I start with the academic theory, ultimately all of my recommendations are going to come from seeing all of these projects. That's going to be that's an important part about us and what we do as a business. Now, the goals of GPS processing, the goals of everything we do really are pretty simple, right? We always think that a good drone program should do a couple of things. It should save time, it should save money, and it should improve your deliverables. So I want to make sure that I get that out of the way first. Again, some of this is a little repetitive if you've seen me talk before, but it's important for everyone that this is the purpose of processing drone GPS, and the purpose of a good drone program is not to be an academic exercise. It should not take 40 hours and a PhD level knowledge to be able to get accurate data. You need to actually get to your end product in a way that saves time, saves money, and gets you high quality deliverables. And that means that good GPS processing cares about, yes, accuracy and data quality. That is important, but that is not the sole goal of good GPS processing. It needs to be efficient in the field. It shouldn't require going up and setting up base stations and marking the location of your base station days or weeks in advance or anything. It should care about efficiency in the office, what actually is easy, simple, reliable to process. It should care about reliability, which means it should work the first time, every time, ideally. And in order to do all of this, you have to balance competing factors. That is one of the themes across everything that we do here. Really, it's a theme across business that I think too many people overlook. You have to balance the efficiency of how much time it takes to do a project versus the accuracy versus the reliability. And there are so many trade-offs in all of this. And ultimately, my goal is not even to tell you exactly what the right Goldilocks zone is for you, but rather acknowledge where the trade-offs are so you can say, hey, this project is accuracy at all costs, even if it takes huge amounts of time and money and it requires very specialized setups and vice versa. So my goal is to acknowledge these trade-offs and help provide my recommendations for what a good middle ground might be. So a good workflow that we say, this is, again, before we'll get into the technical stuff, which will come very, very soon, we always say that a good workflow should do a couple of things. Number one, it should be simple. A lot of what we're going to cover the really in-depth technical knowledge of this, but also you don't need to know exactly how to do carrier phase wave disambiguation in order to actually get accuracy. It also should be robust. We're a big fan of having a single workflow that can work across the majority of sites. As we'll cover, there are truly an infinite number of different permutations of ways that you can set up a GPS system with your drone. And that's good. And there are different systems that might work in different circumstances, but a good system should be robust and work across different circumstances. And that also means trying to make something as standardized as possible. You can always customize things as much as you want, but to make something reliable, it should be standardized. Now, another thing that I want to start by covering really quickly is what is the achievable accuracy of high quality GPS? Or, if I'm being more technically precise, the achievable accuracy of high quality GNSS. GPS is just the United States system of GPS. The absolute maximum theoretical precision of GPS is 8 millimeters horizontal and 15 millimeters vertical, plus 1 part per million of baseline distance. That's the theoretical level. However, that is not how things work in the real world. To get that level of precision, 8 millimeters horizontal, 15 vertical, you need very long occupation times, typically on the orders of hours, as well as very short baseline distances. In the real world, 1/10 of a foot is probably about the maximum real world accuracy of drone GPS. There are ways to exceed it. You can get up to about 7/10 or 7/100 of a foot is about the best you can realistically get with drone-based GPS. Anything in excess of 7/100 of a foot, you're going to need non-GPS solutions for accuracy. And I should also point out another mistake that a lot of people make when they say, oh, the GPS, the RTK on the drone is capable of 7/100 of a foot. That is the accuracy of the antenna, not the drone or camera, or more importantly, the point on the ground after processing. Even if your GPS is perfect, there are plenty more steps in processing to create a map that you should be aware of, but that's not really the topic of what we're covering today. But again, I just always like reiterating, it is important to find balance between accuracy, efficiency, reliability, as well as finding out the balance of the right workflow for your equipment, your project site, your people, your needs. You may work with, or for all I know, the person on this call may be a PhD in statistical analysis, and you don't need me to tell you which softwares to use, but not every company has that. So finding the right balance of the workflow that works for you and your company is there. And obviously, again, the goal of the goal of Aerotos, the goal of what you want to do here is not to create perfect GPS data, it's to create a map. And this is sponsored by Aerotos, so you get the 1-minute plug that we do everything that we're about to cover as a service. Aerotos, we produce drone data processing for land surveyors. You just fly a site, send us the raw GNSS data, you send us your ground control points if you have them, and what you need. We do photogrammetry, LiDAR processing, topographic mapping, planimetrics, the whole 9 yards. If you're interested, reach out to us. This is what we do all day. That's what pays for webinars like this, to be able to share this technology. We obviously try and give as much information out as we can for free, but this is what actually funds the ability to do a lot of this research and put these together. So without further ado, let's actually start diving in to that academic side, the base level technology and definitions, to make sure that we're all on the same page. And we are going to start with the definition of GPS in general. And that is already one of the first common misconceptions. And there's so many acronyms. I'm actually going to go through them and acknowledge which ones are used differently. When people say GPS, GPS is actually just the American system of a GNSS system, which stands for Global Navigation Satellite System. Here are the 4 major GNSS systems out there. There are a few other, I think there are 2 other minor ones, like Japan has one, and I believe India has one. But these are the 4 major GNSS systems out there. They are all run by nation states. So the United States with GPS is generally considered to be the most robust, advanced, and reliable one. There also is GLONASS, which is Russian, Galileo, European, and Baidu, which is Chinese. They are all technologically capable of doing very, very similar things, but the overwhelming majority of the United States, at least, which is where we work, is going to be focused almost exclusively on GPS. A lot of people use GPS and GNSS interchangeably, myself included. I refer to, in general, satellite mapping as GPS, even if I sometimes mean GNSS. But here's your information if you want to use different ones. More advanced GNSS systems are able to use all of these different satellite networks simultaneously, but you typically don't need to. In the United States, GPS alone is going to be more than good enough. And now we need to get into the next thing, which is differential GNSS or DGNSS, which is what a lot of people, again, myself included, also refer to as RTK. When most people say RTK in drone surveying, what they're actually meaning is DGNSS. DGNSS, differential GNSS, also called RTK sometimes or PPK sometimes, is technically the broader term for high precision GNSS processing that uses a base station and a rover, a fixed known position and a moving unknown position. And that is as opposed to single point positioning or SPP. That is just plain vanilla or standard GPS. If you pull up your phone and it gives you a blue dot on the map, that is what's called single point positioning. It is not correcting versus a base station. Whereas DGNSS, differential GNSS, is characterized by having a fixed base station. That means one base station, and it is calculating the differences in carrier phase ambiguity resolution. It is calculating the differences in those waves from the base station to the rover, the fixed non-moving base station and a moving rover. That is the way that it's done. Here is basically your simple sat version of what this would look like, where you do have, let's see if I can get my virtual laser pointer here, I think. Yep. You have your base station, which is going to be fixed. And sometimes, for the record, this is a permanent base station, like one that is run by the US government, like a core station, or a base station that you set up on the site. And then you have a rover that goes with it. All of them speak to the same, communicate with the same satellites, and it resolves the ambiguity in the waves to get very, very high precision data by comparing these two. That is the basic concept of differential GNSS. Like I said, when most people talk about RTK, or PPK, what they really mean, or at least what they're trying to say, is differential GNSS that uses base and rover to calculate the differences. With drone GNSS, things get just a little bit more complicated because there's usually a third step to it. You start with a drone plus its GPS or GNSS, or typically a dual band GNSS system, which is something that I didn't even cover. In fact, that was on this prior slide. There are multiple bands of GNSS that operate at different frequencies. Typically, when we talk about RTK or PPK or any survey grade GNSS, they will use multiple bands, L1 and L2, whereas more routine things like your phone might use a single band. So dual band GPS or dual band GNSS is generally going to be more robust and accurate. So you have your drone plus its GPS system, and on top of that, you might have this little, if you can see, there's a little top hat on top of the drone. That is going to be your high precision dual band GNSS receiver. That is almost always going to be the rover. In most circumstances, when you are operating a high precision drone survey system, it will connect to directly or be post-processed against a local base station, which is the base. However, most circumstances then also will correct that local base station against a permanent base station by way of either an Opus solution or doing post-processing on that local base station. So here's where things already start to get a little complicated. because when you are processing the base station that is on the site, your local base acts as the rover in a DGNSS environment against the permanent base station, which is the base. And then you reprocess the drone against the local base station. So it's multiple steps in order to actually get top tier accuracy. Now, it is possible to connect a drone GPS directly to a permanent base station over here. We don't recommend that, and I'll get into why for a little bit. It is possible to do that via network corrections or PPK only against permanent base stations, but drones are very sensitive to longer baseline distances than ground-based surveying is. I'll cover that in more detail in a little bit, but just for right now, acknowledge it's possible to do that even though we don't recommend it. So why are we talking about DGNSS and RTK when we could be talking about something else? Let's see here. The drone I fly is a Phantom 4. We got a question. Thank you. Phantom 4 RTK. The new coordinates are to the pictures. X and Y is good, but the height is wrong because of the departure height of the drone. Wow, that's a question that I should say reach out to us. It depends on so many settings about what base station you're using, whether it's set up over a local known point, what geoid or ellipsoid height you're using for that. Go ahead and reach out to us afterwards for that question because it's very project specific, but I'll cover more of that later in the presentation. So why are we using DGNSS in general? Why are we using differential GNSS? Well, for a number of reasons. Most importantly, it's more accurate, but there's more to the data than just the accuracy, because you can achieve this level of accuracy using ground control points. It's also more reliable. I say more reliable in the sense that site condition. For example, if a ground control point blows away in the wind or gets damaged for whatever reason, using RTK or more, again, I'm falling prey to my own things. I'm calling it using RTK, even though technically what I mean is using DGNSS. But processing with differential GPS systems makes a job site more reliable so that it is less subject to any errors on the ground. It prevents errors in, for example, imprecise camera calibration that used to happen on old non-RTK drones. It also enables you to fly larger sites with less ground control and more accuracy overall. And it is overall less reliant on ground control points. And of course, that means that it saves you a lot of time in the field and it can save time in processing. The drawbacks are, number one, it is more expensive. You do have to pay for equipment with dual band GNSS that is RTK capable, although those costs have come down just materially over the years. You can buy the Mavic 3 Enterprise with RTK, which is the one drone pictured there, for, I mean, the full system drone RTK base station, everything you need is $10,000 or less. But it does take more equipment. You typically do need a base station. And as we are talking about today, it is a little bit more of a complex workflow. Next up, I want to talk about definitionally the difference between RTK and PPK. Real-time kinematic is what RTK stands for, and post-processed kinematic. Kinematic, the K in both of those, all that means is moving. That means that the rover is going to be moving relative to the base station. And RTK and PPK, the differences are real-time or post-process. So one is done live in the field, that's RTK. PPK, post-process in the office after the fact. Mathematically, they are very, very similar. Not identical, but very, very similar. As far as the trade-offs go, the accuracy is not going to be materially different between the two. We've done a lot of tests. PPK is not like overwhelmingly better accuracy. In fact, in the great majority of cases, PPK has the same level of very high quality, very good accuracy as RTK. The benefits of RTK, and the reason why we really encourage surveyors to use real-time kinematic, is because it gives you real-time knowledge of any errors that are happening in the field. Anyone that's flown or worked with RTK data in the field knows that their system might give them a beep and say, hey, we just lost a fixed integer solution. Wait a second, and then it beeps back and you're in the green and you're good to go for whatever reason. Maybe someone next door turned on a microwave and it caused wireless interference. But RTK really, from an operational reliability standpoint, gives you real-time knowledge to make sure that your system is working properly. Post-process, Sometimes that's the only option. In fact, there are a lot of drone systems out there that are not capable of real-time systems. The leading systems being DJI. DJI is, of course, the market leader in all of this. They are able to do real-time kinematic as well. So we strongly encourage real-time, if for no other reason than in the field if the system goes down for whatever reason, and you can refly a site and save yourself field revisits. That's one of the quickest ways to save time and money in general, is just to make sure that you get the right data the first time. But again, there aren't any huge accuracy trade-offs. They're all pretty similar. One of the ways that post-processing is typically done is with what is called the NOAA CORS network. So CORS, NOAA is the National Oceanic and Atmospheric Administration, and CORS refers to the continually operating reference stations. These are permanent GPS or GNSS base stations that are spread all throughout the United States that are publicly available, permanent fixed location base stations. They generally, but not always, have very high quality data, but they are not always reliable. Sometimes some of the systems are online. They're great for using post-processing, but they're typically not going to be available in real time. They're used for post-processing as well as for the Opus network. This is what most things, when people talk about remote systems, they're going to talk about using the CORS network of publicly available base stations as correction data for anything else that they have in the field. There are plenty of other network corrections systems out there. There are state-sponsored networks, including Texas, Washington, Michigan, Florida, North Carolina. I am not familiar with the ins and outs of every single state correction system. I know they vary extremely widely in terms of their data quality, data availability. If you want to correct against state networks and you have a good quality state network, great, go for it, but not everyone does. So I can't talk in too much detail about each one of those in general. There are also a number of private network correction systems out there, things like Trimble VRS Now. VRS stands for Virtual Reference Station, which is where they actually kind of create a synthetic base station using some statistical averages of other base stations. I don't like those for drones. In general, I can actually tell you these other network correction systems typically have baseline distances that are too long to get the level of accuracy and precision that I would like to see out of drone systems. It is also worth noting that these private network correction systems are streamed via something called NTRIP, which is the networked transport of RTCM via Internet Protocol. And here we have some of our Russian nesting dolls of acronyms, because RTCM via Internet Protocol actually stands for the Radio Technical Commission for Maritime Services, which is the format that the GPS data is encoded to before it is streamed over the NTRIP protocol. Now, I'm not trying to get too technical for all of this stuff, but this is part of why there's so much confusion, that a lot of times people will download GPS data and it'll be in RINEX data, which is going to be a GPS file format, but sometimes it's streamed or it's stored in RTCM3 format, which is this Radio Technical Commission of Maritime Services. There's so many different formats, and everything uses these obnoxious acronyms that people get really confused over. So NTRIP is usually used as a way of saying that it's GPS data that is streamed over an internet connection, GPS correction data streamed over an internet connection, rather than, say, having a local base station or something like that. All right. We got a question out there. When using core stations to mark for GCPs, do I need to take measurement and repeat after 20 minutes to get very accurate GPS coordinates? What we're talking about there is the general concept of occupation time. How long of an occupation time do you actually need on a ground control point or something to get accurate data? And the short answer that I would say to that is it really depends on your setup and on your baseline distance. If you are doing an Opus solution, for example, and we'll cover Opus, I think, next. Oh, yeah, exactly. That was my next slide. Opus is the United States Online Positioning User Service. This is what people typically use to set up their base stations on project sites. This is where you set a base station up over an unknown point, continuously record data for typically a couple of hours, submit it to Opus. It performs DGNSS corrections across multiple different base stations, and then provides you with a single fixed location. And what we have here on the right is actually the chart of accuracy of an Opus solution based on occupation time. And this is where your occupation time really depends on your accuracy. So an Opus solution for 20 minutes will have about 6 centimeters worth of root mean squared error. Whereas if you really want to get down to that, sub 10th, call it, couple hundredth accuracy, you typically need a 2 to 3 hour occupation time for a really high quality Opus solution. Again, that very much depends on baseline distance to the core stations that it's used. Just had someone point out, typically surveyors establish site control prior to a topo drone survey, and site control is already completed through Opus's end cores. It sounds like you may do that, but I work with a lot of surveyors that don't. The way that a lot of surveyors that I have worked with, and this is why we talk about this workflow, because there are different options. One way is to establish site control prior to the topo drone survey and already complete it through Opus. The other alternative that results in fewer site visits is you go set up your base station where you will be collecting an Opus solution and fly the drone on the same day and post-process all of it. You will still get an Opus solution for that base station, and then you will create your control based off of that, and then you will use that control in the solution. So you can set up a Opus solution on a day before or prior to flying the site, but a lot of times we've actually seen it the other way around, where someone might set control, fly the drone, and then do an Opus solution and mark the control after the fact. You actually can do it on either the same day or in different orders, as long as you get your data processing right. So that's awesome. If you want to establish your site control and get your Opus solution before the drone survey, great. There's nothing wrong with that, but you don't actually have to do it that way. There are other ways, and we see surveyors that do it totally different ways. All right, I'm going to keep going because I don't want to make sure we don't want to run out of too much time. What base station should you use? Well, there are a lot of different ways you can do it. The old way to do it is not use any base station whatsoever and rely only on ground control points. This is what was done before RTK was, before DGNSS, I should say, before DGNSS was readily available on drones. This is no longer the recommended way. Now there is RTK. I think RTK should be considered mandatory. For local base stations, you really have two options. A first-party base station like a DJI DRTK2 made by the manufacturer. It streams differential corrections to the drone. That is all it does. It should not be treated as a separate rover or a substitute for a Trimble RS-12 or anything like that. Or you could use a third-party base station. And lastly, you can stream data directly via NTRIP, via that network protocol, to your drone from a permanent base station. Again, I don't recommend that. The baseline distances are long enough that because the drone is moving at 30 feet per second, if it has any sort of noise in that measurement, it can't stay and occupy the same point for 5 minutes or 10 minutes or anything like that. So we don't recommend network corrections. We strongly recommend having a local base station for a drone. We also often get questions, how does the DJI base station work? It's kind of like, it's not going to be Trimble quality, right? No, it's not Trimble quality, but the reason we like it is because it is dead simple and you can train an employee how to use it in the first day. To turn on the DJI base station, to work it, you just turn it on, it calculates an arbitrary point, and all RTK calculations are streamed to the drone relative to that point. The base station data is recorded in RTCM3. It can be exported and post-processed as well, but it's kind of a pain. And the geolocations encoded to the imagery are typically very precise, but not accurate. You do not need to set it up over an arbitrary point or over a known point. You can set it up over an arbitrary point and post-process it after the fact. As for the Trimble's base station or any third-party base station as well, you actually can connect it in real time via an NTRIP connection. You can connect it to a drone, including to DJI drones. It's just kind of a pain because that's not what these systems were designed to do. The data quality is absolutely great. It is, quite frankly, comparable to the DRTK2, if not ever so slightly better, but it's a very, very, very complex field workflow because you have to figure out how to properly get your base station and data collector to encode the stream of GPS data in that RTCM3 format and stream it to your base station via the N-trip internet protocol. It's a complicated workflow. If you know how to do it and you're good at troubleshooting and working with those sorts of things, go for it. It's different for every base station, and I find it to be really, really frustrating. Yes, you can do it with like MLID systems, Trimble systems, Leica systems. Any of those work as a base station, as a local base station that can stream the RTCM differential GNSS systems. But we don't like it. We actually prefer the DJI base station, again, just because it's stupid simple, and that leads to that more reliable workflow. But high quality accuracy is very capable with both of those. All right. Let's see. We are getting a lot of questions. So, Mike, I'm going to call you in and see if you've been reading those, because I've been looking at other stuff right now. If there are any good questions that you want me to address right now.
I think we'll probably be getting to a lot of these just based on the content.
Cool. Then I will keep going as well and jump actually right into what is the GPS system setup. Now that we have a little bit more better shared knowledge of the different ways and parts of things work, let's get into the setup. So the major considerations when designing a system setup for your drone GNSS system are, number one, the drone and its onboard GPS and or RTK antenna, the base station that you use and where to set it up, what ground data you have in advance, whether you have ground control points or not, and whether you have a known location for a base station. This goes to what we were talking about before. Do you get an Opus solution on a known point before you fly the drone or not? As well as what processing workflow you plan to use. Are you going to use real-time versus post-process, or are you going to do one of these multi-stage steps that I talked about where you get an Opus solution on your local base, which is processed against a permanent base, and then use that to actually correct your drone data as well. So those are the main considerations. For starters, let's touch briefly on drone hardware. Hardware absolutely does make a difference. First of all, I've mentioned this before, we've gotten to a point in drone surveying that any surveyor that is buying or using a drone should consider RTK to be mandatory. If you are buying a new drone, do not buy a non-RTK drone. That's ridiculous. Quite frankly, if you own a non-RTK capable drone, or rather a non-DGNSS RTK or non-DGNSS capable drone, it's probably time to upgrade. The first good one, the Phantom 4 RTK, came out in 2018. We are now 6 years past the introduction of cheap, available, survey-grade GNSS on drones. It's time to upgrade. Buy an RTK-capable drone if you haven't already. However, there is a lot of misconception. Buying an RTK-capable drone does not mean that accuracy is immediately good. There are lots of people out there that will buy an RTK-capable drone with an RTK antenna or a dual-band GNSS antenna on it and not realize that you need to set up a base station, connect it to that base station, and actually have that differential GNSS calculation performed somewhere to get good accuracy. Just because you bought an RTK-capable drone does not mean you are getting RTK or DGNSS level accuracy on the system. I should also point out, more expensive absolutely does not necessarily mean better. One of the interesting ones up here, for those that remember, this system right here was the DJI, it was the Matrice 210 RTK, and it had RTK in the name, so everyone thought it was going to be highly precise. But it was completely worthless from a survey perspective. It did not have the data in the right format. All it was used was RTK was used for navigational purposes, not for calculating the image center at the time the shutter was taken. That drone is no longer made, but it's just to point out, just because someone says a drone is RTK capable and because it's very expensive does not necessarily mean it's good. Systems like the current DJI drones, the M350 RTK, the Mavic 3 Enterprise, this is the Wingtra RTK is there as well. And even the latest generation of Autel RTK drones are much better. I still actually think the RTK implementation on the DJI Mavic series is better than the Autel ones, but that's a little bit beside. But more expensive to not necessarily be better. And as I've said with a lot of hardware things, anything that isn't DJI does come with trade-offs. All I ask you is, if you are not supremely confident about the technical capabilities of a system, please consult with an independent expert first. If you're curious, always reach out to Aerotos. We're happy to give our data processing focused perspective on this, of what the right drone is to buy. You can ask us and we can give you an independent perspective, because we've seen too many people buy drones that claim to be RTK capable, but the implementation is just awful and leads to a lot of noise. All right. We already talked about this a little bit. What base station do you need to use? We recommend you do need a local base station, one of these in the middle, first or third party. The DJI is our favorite because it is just simple to use. Any third party one gets you great quality data. Just make sure that you know how to troubleshoot it in the field. Another common question when figuring out a setup is, great, so I'm spending all of this money and time. I've got my base station. My drone has GPS. It is capable of getting accuracy down to sub-tenth of a foot on the image geolocations. Do I actually need ground data? Do I need ground control points or anything like that? And I should point out that very good RTK and PPK is technologically capable of producing survey-grade accurate maps without ground control. However, we are very strongly of the opinion that no control, or rather no check shots, is not good enough. That is because ground control is required to do things like properly calibrate a camera to make sure that even if your image center on the camera image center is correct, the reproduction of the ground based off of the photos is correct, because camera lenses can be subject to even changes based on temperature. You also probably need to localize your projects. A lot of projects, you set up your base station over a pre-existing known point that may have been marked 20 years ago, and you localize everything to there. Or maybe you've even shot your control on a 5,000 grid using a total station. You need ground control to localize that. And of course, most importantly, having the ability to detect errors, which there are just human errors throughout every step of any process that involves people. Human error does remain very common in complex RTK and PPK workflows. So even though good GNSS does not technologically need ground control data, we think that it is very important for surveyors to do that. Another huge benefit of RTK when you're setting things up, good RTK very much can compensate for fewer GCPs. This project right here, you can see there are only 3 blue dots that are ground control points in this upper corner. However, we ran this with only 3 ground control points and check shots throughout the entire site. As long as you have very good, robust RTK or PPK, the accuracy of a system, assuming that all of the photogrammetry and or LiDAR processing is done well, is still very good, far outside of the pattern of ground control points there. So good RTK can very much help with that. The next topic I want to talk about with RTK and PPK is this concept of accuracy versus precision. Most of you have probably seen this chart, in fact, maybe many times over the course of either my presentations or other presentations. Accuracy versus precision. And we'll focus on these ones on the right. This one here, where everything is close together, is low accuracy and high precision. This low accuracy, high precision is what differential GNSS, DGNSS gets you by default. High accuracy and high precision is when you have a known base station location and short baseline distances. So what does this mean in the real world? Let's talk about it. Precision, where you get everything very close together, happens when you have RTK or PPK to an arbitrary location, local base station. That's what happens when you set up on a job site by default. You take your base station, put it over an unknown location, and fly your drone. If you were to process it without any further post-processing, this is what you would get. To get accuracy, to get this precision moved over towards the center, which is what you want eventually, there are a couple of ways you can do it. One, you can use ground control points so that you take that whole project, shift it to your known ground control points. You can program the local base station over a known point if you have a known point in advance. That can be a little bit different because it depends on whether you actually have that known point in advance, especially if operationally you have to move it to different points on the site to take off from different locations. So that's not always feasible, though sometimes it is. You can get your Opus solution on a base station as well. Those are some of the systems that get you accuracy, whereas RTK or PPK to a local base station only gets you that precision. So the question is, where do you set up your base station? Well, you could set it up over an arbitrary point, which gives you precision, but you do need that ground control point or further post-processing for accuracy, which can be made accuracy with PPK of that base station or an Opus solution. It does require some post-processing, though, to get it. It's not just right out of the box. You can't just throw those photos into a photogrammetry suite and expect accuracy. You'll get precision, not accuracy there. Or you can set it over a known point where that's been previously surveyed. You code it into the base station as it's setting up and streaming those corrections. That is very wonderful if you have it, but it's a slightly more challenging field workflow. It does typically mean that you need to have a surveyed known point in advance, which again, that's challenging workflow. If it means you have to go to the site the day before, you can do that, but that's an extra site visit that a lot of businesses don't want to do because it costs time, it costs money. You don't always have access to the site on multiple days. Sometimes you just want to get in, get everything done in one day. So your only option is an arbitrary point, and that can totally be handled. One of the big challenges, though, is if you're setting up over an arbitrary point, particularly if you have multiple flights on larger sites, you are setting up on multiple arbitrary points. And what that means is that you will have every time you move the base station, it's going to set up over a new arbitrary point, and the swaths, the individual flights that you do with these different base stations may be offset from one another. And this is super common, in fact. And I should say it's not a problem. This can absolutely be handled in post-processing, but you do need to focus to make sure that your flight segments line up with one another. This is what things can look like where you have flights over a different base station. You get X, Y, and Z shifts, and they just don't line up correctly once you're actually in the field. You can calculate these offsets and correct with them either by using ground control points to offset each individual flight segment. You can do Opus solutions on the base station data when it was set over an arbitrary point, or you could just do dead reckoning interpolation where you actually take these and just say, hey, this one's 5 feet too high, just subtract 5 feet to it and move it, translate it X and Y to get them to line up. Just something to be aware of, but totally manageable in post. As far as what our recommended workflows for all of these are, I want to always give the caveats here, some limits to our recommended workflows. As I've mentioned, all of our recommended workflows do require some level of ground surveying. Yes, you can do it without it, but we think that's really important from just a professionalism standpoint, from an error catching standpoint. There are so many errors, you really want to be able to catch them. So we recommend some level of ground surveying for every workflow. And they're designed to optimize, to find that balance that I talked about before, that balance between accuracy, reliability, and ease of use. And of course, there are often edge cases that require very custom workflows that change based on challenging GPS environments, very challenging site access requirements, different availability for there is no cell service here, can't do all sorts of different things that can require different workflows. There are edge cases. I'm looking for kind of that middle 90% really. There are also a lot of workflows that work that we don't love. Like I mentioned, we don't love doing post-processing only workflows where you are only PPK, no real time, because it can lead to field revisits. It requires a little bit more processing in the field. Setting up a base station over a known point, like I mentioned before, that's great if you have it, but it requires advanced field data, and it raises the barrier to doing drone surveying, and we think drone surveying can be done more easily if you establish a workflow that does not rely on a base station being set up over a known point. Also, when you do rely on setting it up over a known point, you have no in-field flexibility. If that known point was either damaged or you don't have access to it at the site, or you find out you have to move and take off a drone from a different location for operational purposes, setting up a base over a known point doesn't give you that in-field flexibility that arbitrary point processing does. So personal preference there. You could also, like I say, do RTK or PPK direct to a permanent base station via N-trip. We don't like that. Lower accuracy than a local base, and it is complex and error prone, whether it's caused by interruptions in cell service or long baseline distance. It's just not quite there. It's not our favorite thing. Simplest workflow that you can, of course, use the old way, using GCPs only with no differential GNSS. That's the simplest way to do it, but quite frankly, we don't like it anymore. RTK should be considered near mandatory. We've mentioned that as well. Really, you can only use this if you do not have reasonable access to DGNSS equipment. It is simple and cost effective, but it's not going to be the most accurate or robust system out there. Our favorite overall, though, is going to be using RTK plus a local base station with multi-stage processing. That does sound a little bit complicated, and admittedly, it is a little bit complicated. That's where you set your base station up over an arbitrary point, and then you correct the data so that it matches the project site in the office after the fact. The reason we like this is it gives multiple avenues to get both accuracy and precision. It gives a lot of options in post-processing, and it gives a lot of field flexibility. This system, the reason we like this is it works on basically all project sites. It does not require short baseline distance to a core station. It does not require cell access or cell coverage in a project site. It works in a quarry in the middle of nowhere. It does not require access to the site beforehand to set up and set ground control and do an Opus network before even setting up your local base station. This is the most flexible, robust, powerful, and scalable workflow. That's our favorite way to do it. That's what many of our clients do. Take your base station, set it up over an arbitrary point. If you have a known point, great, set it up over a known point, but it's not required. So that's that 3-stage, right? The drone is the rover to the local base. The local base is the rover to the permanent base station. You run those sets of processing, that's what actually gets you there. So yeah, of all of these systems, whether you're using no RTK, PPK only, RTK via N-trip, or RTK with a local base, we really like having RTK with a local base station. All right, now with our, excuse me, with our last 10 minutes, let's actually get into data processing a little bit here. Now, as I've mentioned before, you get your brief spiel of what we do. If any of this was complicated and you don't know how, or any of the data processing is challenging to you, come work with Aerotos. That's what we're here for. You fly the drone, we process the data. You would just set your control, fly a project, upload your data to us, including with arbitrary base stations. And we do all of the GNSS post-processing, photogrammetry, LiDAR, line work drafting, quality assurance, quality control, and CAD integration. So that's what we do. Now let's actually get back in, and you can always hire us. We're always here to work for you guys. That's what we do. Basic processing workflow for actually doing all of this. There are 4 major steps, the 4th step kind of being a doozy here. Number 1 is actually getting your DGNSS processing done, doing the differentials. I apologize if you were expecting to come here and get a PhD level course on exactly the mathematics behind DGNSS processing, but that is not what I am going to talk about today, because that is all done by software. The biggest the biggest software that people use for DGNSS processing is going to be Trimble Business Center. A lot of people like Trimble Business Center. I personally do not. Like Infinity is capable of doing it as well. RTK Post is going to be the most common open source, also known as most common free software out there. RTK Post is very capable of DGNSS processing, but not the world's most user-friendly thing out there. Opus, getting an Opus solution is itself a form of DGNSS processing where you don't actually need to know the mathematics behind it or too much technology or anything like that. Once you get your DGNSS processing done, though, it is worth noting that when you process the raw GPS or GNSS data, what that gives you is the accuracy of the antenna phase center, which is the center of the RTK antenna, at the time that that GPS observation was taken. But that is typically not what you care about. What you actually care about is the location of the image center at the time the photo was taken. And that means you need to do antenna offset and lever arm corrections. Again, there are numerous softwares that'll do this. Trimble Business Center does do this. A lot of other systems, like if you use a Wingtra does this in their proprietary system. All the GeoQ TrueView systems, they have a proprietary system as well that does the antenna offset and lever arm corrections. You can make custom spreadsheets that do this as well. Just be aware that the location of the DGNSS process data is not the same as the location of the image. After you do all of that, then you need to do any arbitrary base station offsets. Again, if you've used multiple base station moves, then you need to offset those on each individual flight. to make sure that they line up with another and that they line up with your ground data. And then you can go into further photogrammetry processing, LiDAR, drafting, all of that good stuff as well. As far as what software you can use for post-processing, like I said, RTK lib or RTK library is what it stands for, is going to be open source and works well, but there is a little bit of a high learning curve. Trimble Business Center is going to be more popular, easier to use, a lot more expensive. A lot of surveyors hate the Trimble ecosystem. Leica Infinity, I know, can do that as well. I personally have near zero experience with Leica Infinity, but it's got people that love that as well. But when we get into manually post-processing and talking about things with RTK library in general, one of the questions is, do you need to manually post-process at all? And this is where we'll get back into kind of that business and operational side of things here. The fastest form of post-processing is no post-processing. And that means if you have set up your system correctly, and maybe you have a local or an arbitrary base station with ground control points, you might not need it, and you use RTK. If you used RTK, you don't have to post-process the GPS stream at all. And that's the simplest way to actually do things and get it done quickly and efficiently. So that's part of why another reason we like real-time. Real-time GNSS processing is done on the drone, and often with a good workflow negates the need to post-process at all. So you almost need to ask yourself, which takes more time, setting control or running an Opus solution on the base? Maybe you're already running this Opus solution on the base. Maybe there's been site surveying done before. These are some of those considerations that are going to be unique to each surveyor and each job site, depending on exactly what workflow you want. There is flexibility. There are options there. And also, having a plan is important. Which parts are you going to post-process? Know all of this in advance. Are you going to process the drone against the local base against static or network base, the drone against static network base? Are you going to offset existing geolocations? It's just important to know it before you fly. And you can post-process all of this over a moving point. Here's just some of the information you need. We've got plenty of blog posts on some of the actual technical nuances of how to use like RTK library. If you're interested in any of those, go ahead and let us know. But ultimately then, and it's beyond the scope of this webinar because we're already running out of time. This is, of course, just step one in processing drone data. You process all of your GNSS data first, and then you can do photogrammetry and LiDAR processing and line work drafting and getting it into CAD and creating a map out of all of that. And once again, that is really why Aerotas exists as a company. We create CAD files from your drone data. It's all professional drafted. We have photogrammetrists, we have GNSS experts, we have all of that stuff. So once again, you fly the drone, you send us the data, and we get that data back out to you. Why you would use us? We, of course, have experienced members. Our team members are incredible. We have the scale to do all of this, the accuracy. We know these projects, and we are reliable and scalable, whether you're doing one project a month or one project a day or even more. We can help you out with that. And of course, if you are interested in learning more, and in fact, if you want to see what we and our data processing can do for you, reach out to us at aerotas.com/contact, and we'd be happy to help. And with that, we've actually got 5 or 6 minutes, so I'd love to start the conversation with questions. So I'm going to go through and start reading these, but go ahead and start actually adding some information in. I saw some people were talking about a PPK workflow using propeller arrow points. Yes, propeller arrow points are actually great. They are perfectly capable of good accuracy. I've actually, believe it or not, known the guys at Propeller for like 8 or 9 years now or something. We've been good friends for a long time. Their system is very, very good. It's just a different workflow. It doesn't work in all systems. It requires longer occupation times. It only works on precise known coordinate systems. It's not as good as arbitrary systems. And it requires using the arrow points, which are typically additional equipment that surveyors don't need. Surveyors don't usually need arrow points, so it's designed for an earthworks application. Propeller arrow points is just effectively, it's just a flat base station. It's a series of base stations that are used to post-process after the fact. They do very, very good data, but they typically aren't the optimal workflow for surveyors. They are the optimal workflow for earth movers, which is why they are successful there. Let's see, we got another question on the MLID Reach and the MLID GNSS systems. MLID GNSS systems are absolutely, completely, perfectly capable of getting high quality GNSS data. They are not without their drawbacks. Their software is a little bit clunky. It is typically not going to be as high quality and reliable as a good Trimble or Leica or Topcon system. They have some cheaper GNSS chips in them as well. If anyone really digs into the clock data on some of those, you'll notice that their clock data is actually, it sometimes gets desynced from GPS time by a few millionths of a second, which might sound weird, like a few millionths of a second doesn't matter that much, except that when the clock gets offset by a few millionths of a second because it's using a U-blocks conversion metric for the actual GPS data, it makes Opus solutions not work. So MLID doesn't always work for getting an Opus solution, which is kind of a pain in the ass, and we don't actually, but that said, yes, if processed right, it totally works. Another question we have, a very good one. How many ground control points can I expect to reduce in a project if I use RTK compared to without using RTK? So if you have 20 ground control points in a given area, how many ground control points do you need with RTK? Yeah, I would say about 3 to 5 is probably the right amount. Our rule of thumb is for any job site that has very high quality RTK processing, that you're using a proven and known workflow, 3 to 5 ground control points is going to be the right number. And every time you move your base station, add another 3 ground control points. That's our rule of thumb. Anytime you move a base station, you want 3 ground control points. There's a little bit more nuance to that. You can see our previous webinar, go into the Aerotos blog if you want that. We got a lot of data about exactly how some of those flight operations go and that sort of thing. Thoughts on using Leica SmartNet to set control and then running a Phantom 4 RTK with GCPs? Yes, that actually works great. So using Leica SmartNet or Trimble VRS Now or any sort of network solution to set control works fantastically. And the reason that works is because when you're setting control, you actually you can set your survey equipment over a known point for a longer period of time. Even if it is just a 5-second occupation time for setting a control point, that gives you so much more data than a fully kinematic, a fully moving drone that's at 30 feet per second. So that actually reduces the ambiguity in the DGNSS solution. So using Leica SmartNet or any similar network solution for setting ground control points, absolutely fantastic. Fully recommended, fully approved by me. No problem with that whatsoever. What software do you recommend for processing the photos? We think Pix4D is the best out there. Is Open Drone Map any good? It's kind of a pain in the butt. It can do good solutions sometimes. Pix4D is more expensive, but it's unquestionably better. Is the Phantom 4 RTK a good drone for RTK? Yes, it absolutely is. Those things are workhorses. If you got a Phantom 4 RTK, no need to upgrade. That thing is absolutely good. Question about where is the DRTK2, the DJI base station, where is its ARP or antenna reference point? I don't remember. They have documentation for that online. I'd have to look up. Every single base station has its own antenna reference point offsets. That information is out there online. You got to look up the individual manufacturer's user guide and look for their diagrams on exactly how far offset the antenna reference point is from there. Okay. Thank you so much for the questions. I did not get to all of them as promised. I hope this was useful to you. Please keep asking questions, or like I said, aerotos.com/contact. You can email your questions directly to me if you want. My email address is logan@aerotos.com. Please keep them coming because it is your questions and this information that actually tells us what we should do for our future webinars. So we are now at 10:59. It just ticked over to 11 o'clock Pacific. Thank you so much for joining us today. I appreciate it. And we'll be having another one of these in the future.